In the last video, we've seen that atoms emit light when they recapture free electrons. The reason that light is emitted is because electrons falling into an energy well have to release their excess kinetic energy somehow. You might recall that the formula for kinetic energy is 1/2 mv squared. What this formula tells us is that if the velocity of an electron changes, then the kinetic energy of the electron has to change too. In fact, the same formula applies for both electrons moving through free space and for planets moving through our solar system. Anytime there is a change in velocity of a moving object, there must be a change in its kinetic energy. If the velocity of a moving object remains constant, then the kinetic energy will not change. But because we also know that acceleration is the rate of change of velocity with respect to time, then we can conclude that any object which has a non-zero acceleration must have a source of energy to boost its kinetic energy, or any object that's decelerating must somehow get rid of its extra kinetic energy. In the case of the free electron, inside the plasma of a lightning bolt, that excess kinetic energy is released as light. The key concept here is that objects which are accelerating emit or absorb energy. Let's consider two examples, one from electromagnetics and one from gravitation. First, electrons spiraling around an atom from a higher orbit to a lower orbit. You could imagine that the diameter of the orbit of an electron around a proton in hydrogen must be very small. So the electron jiggles back and forth in its orbit trillions of times per second. An electron being shaked back and forth is accelerating, and energy is emitted in such a situation. Consider electrons spiraling inwards from a high orbit to a low orbit. They jiggle back and forth 600 trillionths of times a second, emitting light at 600 terahertz frequency, for instance, which our eyes interpret as green light. If you take the speed of light and divide it by the frequency, then you get the wavelength, and the wavelength corresponds directly to color. Another situation, example B, where electrons emit energy is where radio waves are emitted from an antenna. All you need to do to create a radio transmitter is to shake electrons in a metal antenna up and down at the appropriate frequency, and you'll generate a radio wave at exactly the jiggling frequency. The entire electrical municipal supply in Singapore and continental Europe operate at 50 Hertz alternating current, AC. This means that the Earth has a strong radio glow at 50 Hertz. Let's now consider a single electron moving up and down in a sinusoidal manner inside a copper wire. If I call the position Y, then y is a sine wave with respect to time. The velocity is just the derivative of position with respect to time. If you've not had a class in calculus yet, it doesn't matter, because it's obvious that the velocity must be changing continuously, and that's the point I'm trying to make here. Furthermore, the acceleration of an electron in a copper wire is also not constant. It's just the derivative of the velocity with respect to time. It's clear here that an electron is accelerating in a sinusoidal way. So a radio wave will be emitted from an antenna also at a sinusoidal frequency f. Let's now consider what happens in a gravitational system. And instead of considering an electron in orbit around a proton, let's consider the Earth in its orbit around the Sun. I've now crossed out the word Newtonian because if accelerating objects emit energy, then we know that the Earth's orbit cannot be stable. It turns out that if you accelerate masses, then you generate gravitational waves, analogous to the situation in which accelerating electrons generate electromagnetic waves. This concept is not difficult to understand, and it forms the basis of the theory of general relativity. In example A, the Earth is orbiting the Sun once per year. You can work out how many orbits per second this corresponds to, and it works out to 31 times 10 to the power minus 9 orbits per second, or an orbital frequency of 31.7 nanohertz. So that's the frequency of the gravitational wave that the Earth orbiting the Sun emits. And because the Earth is emitting this gravitational wave continuously, the orbit of the Earth is not, in fact, stable because it carries away some of that energy from the gravitational wave every orbit. So the Earth's orbit is actually spiraling inwards ever so slightly. And I've calculated here how much it is spiraling inwards due to this energy loss. It works out to be about 0.349 picometers per year. That's less than the width of a proton, but it's there. And that's the effect of general relativity on the Earth's orbit. If we wait long enough, then eventually the Earth's orbit will decay and the Earth will spiral into the Sun because of this. But it's going to take longer for that to happen than for the Sun to turn into a red giant and swallow up the Earth anyhow. So it's not something that we're ever going to need to worry about. But gravitational waves have been detected, and the effect is real. The first gravitational wave was detected in 2015. It was emitted by two black holes orbiting each other 75 times per second before they merged. They merged in 0.2 seconds. I think it's very interesting, and that's a complete departure from Newtonian gravity, which says that orbits are completely stable forever. There's one major difference between the orbits of planets around stars and the orbits of electrons around atomic nuclei. And the difference is that electrons in orbit around atomic nuclei can be stable in certain orbits. If this were not the case, then electrons would emit electromagnetic waves and spiral all the way into atomic nuclei, and atoms wouldn't be stable enough to exist. Obviously, that doesn't happen. And understanding this was one of the great achievements of quantum mechanics. It's beyond the scope of this class to explain why. But I think it's not so difficult to understand that electrons which change from one orbit to another have to emit energy in the process. I've plotted the first few stable orbits of hydrogen against a side view of a stretched fabric electronic well. And for comparison, I've also plotted the gravity well showing the orbits of Venus and Earth in the solar system. You might recall that the vertical axis here represents potential energy, and that Venus would require more energy to escape the solar system than the Earth would, because it sits in a tighter orbit with less potential energy than the Earth to start with. Normally, an electron in a hydrogen atom will remain forever in its lowest orbit, called the ground state, which I've labeled here n equals 1. If I impart a large amount of energy to that electron, then the electron should be able to escape the atom completely. The energy needed to do that is called the ionization energy of hydrogen. One way to give energy to electrons in orbit around atoms is to apply an external force, for example, by putting a high voltage on nearby electrodes which will pull on these electrons. Another way would be for free electrons to impact the atoms and give them some of their kinetic energy. We saw this in the case of the ionization in a lightning bolt. A third method of giving energy to atoms is to shine light on them. An electron is only permitted to absorb energies in fixed amounts or quanta corresponding to the distances between the green lines on this graph. So if an electron is happily orbiting a proton at the n equals 1 level, and I attempt to give a little energy to that electron, but not enough for it to make it to the n equals 2 level, then the electron will not absorb the energy and nothing will change. If I give exactly the right amount of energy corresponding to the difference between the n equal 1 and n equals 2 levels, then the electron can absorb the energy and its orbit will be raised to the n equals 2 level. And of course, when electrons fall from one orbit to another, they would then have to get rid of that energy somehow by emitting light, for instance. In the gravitational situation, it's unknown whether orbits are quantized or not. That's one of the big open questions in science and physics, but at the enormous distances in our solar system, there is certainly no discretization, and all gravitational orbits are basically allowed. Venus and Earth just happen to be at the orbits where we find them due to the way that the solar system formed. There's nothing special about these orbits. But it certainly isn't possible to alter a planet's orbit without some form of energy change. Let's take a look at the allowed electron orbits in a hydrogen atom now. Each arrow on the diagram represents a possible transition of an electron from one allowed orbit to another in a hydrogen atom. So the length of each arrow represents the energy which must be emitted as light if an electron makes such a transition. Now, it's worth pointing out that most of the time you will only find an electron orbiting in the lowest energy level in a hydrogen atom, the ground state. It's not so common for an electron to be in orbit in one of these upper allowed orbits, because then it would naturally spiral into the n equal 1 level and emit light in the process. Energy on this diagram is referenced to the energy of a free electron at the top of the diagram. All energies are negative because an electron needs to lose energy if it falls into orbit in a hydrogen atom. For example, a free electron up here, which is captured by a proton, must lose 13.6 electron volts of energy to reach the ground state in a hydrogen atom. This is called the ionization potential because conversely, if an electron is already in the ground state, this is the same energy we need to supply to the electron to get it to completely escape the hydrogen atom and create an ion, which is just a proton in this case. These energies can be converted into frequency with the help of Planck's constant h, and frequency can be converted into wavelength or color with the help of the speed of light. Let's look at a couple of examples. Firstly, an electron in the n equals 1 energy level, the ground state of hydrogen is stable. It will not decay to a lower orbit and thus has no energy to give up as light. But if an electron happens to be at the n equals 2 orbit, then it would need to release 10.2 electron volts of energy to get into the n equal 1 orbit, because 10.2 electron volts is the difference between minus 3.4 and minus 13.6 electron volts. A 10.2 electron volt photon has a wavelength of 121.6 nanometers, which puts it into the ultraviolet range. But quite a number of the allowable transitions of an electron between the various orbits are actually in the visible range. So an electron hopping from orbit to orbit will emit quite a number of different colors. I should also mention that once a single electron is in orbit around a proton, a second electron will not come along and occupy one of those other orbits. That's because the electron carries its own negative charge, which balances out the positive charge of the proton that's already in orbit in a hydrogen atom. A free second electron hypothetically lurking around near a hydrogen atom will not be attracted to it because a hydrogen atom is electrically neutral as a whole. Basically, electrons repel one another. This is different for the force of gravitation, which is always attractive, which causes mass to tend to clump together. Again, for the gravitational force, we don't know whether there is quantization or not. We also know that planets in orbit around stars do slowly spiral inwards, releasing gravitational waves. And this is not predicted by Newtonian gravity, just as classical electromagnetics does not predict the quantization of orbits there either. These transitions form something like a fingerprint for atoms. So it's possible to detect hydrogen, for instance, by analyzing the colors emitted. By looking at the spectrum of the sun, for example, it's possible to see that it contains hydrogen. This is an example of a spectrum as observed by George Hale at the Mount Wilson Observatory in 1917. The horizontal axis is wavelength here, and the discretization of the spectrum is really clear. In fact, when scientists started studying the sun's spectrum, they noticed some lines which did not correspond to any known element. So they named the unknown element helium. The Greek prefix helio means sun, because helium was first spotted on the sun before it was ever discovered on Earth. By the way, helium is the second most abundant element in the entire universe, but on Earth, it's a very rare, precious, valuable resource. You can only get it from natural gas mining, and there's not very much of it left. During my lifetime, the price of helium has risen by orders of magnitude, and we're very lucky to still be able to buy it and fill our party balloons with it. And it might be the case that during our lifetimes it could become impossible to buy helium for party balloons anymore because it might become too valuable. It's needed for magnetic resonance imaging and as a coolant in superconducting magnets. This is a portion of the Hubble Deep Field, a very famous photograph. Astronomers aimed the Hubble Space Telescope at an area of dark sky and ran a nearly 30-hour exposure, and thousands of distant galaxies were found. Some of the galaxies in this photograph are over 13 billion light years away. It's amazing that the universe is so transparent. It's amazing because the universe contains quite a lot of gas molecules. In fact, there was a time when the entire universe was full of neutral gas. If you try to shine light through gas, it's not very transparent for far. You get scattering. On Earth, the sky is blue due to scattering. If you try to look through any column of gas, you can't see very far because light ends up being scattered, and scattering is almost like being absorbed and then re-emitted, absorbed, and then re-emitted again. In this way, it's difficult for light to travel in a straight line. Yet, in spite of quite a lot of gas in outer space between us and the galaxies in the photo, the universe is transparent. Why? What it comes down to is that all of the atoms floating around in space are already ionized. Their electrons have already been stripped away. That is to say that outer space is not full of neutral gas, but ionized gas. But during the first few 100 million years, from approximately 150 million years after the Big Bang to 1 billion years after the Big Bang, during a period of 850 million years, most of the gas in the cosmos was neutral, so space was not transparent during that time. The sky would have looked very hazy in all directions then. But once light from the first stars began shining, it took only a few million years for all of the neutral gas atoms floating around in the universe to become ionized. This great event was called the Epoch of Reionization. Here are a few learning points from Part 6. First of all, strong electric fields created by high voltage differences can ionize gases. Light of the appropriate wavelength or energy can also ionize gases. When electrons move from one orbit in an atom to another, light is emitted. Thirdly, each chemical element has a different set of allowable energy levels. In the next video, we'll experiment with a two-electrode setup and we'll see for ourselves how different gases spark differently.